Okay. Hello, everyone. I'm Renee Yager, the Director of Marketing at EPC, and welcome to today's Summer of GaN webinar. This is GaN First Time Right, controllers, gate drivers, and PCB layout tips for DC-DC converters and motor drives. Before we get started, I would like to go over a few housekeeping items. You will have the opportunity to submit text questions by typing your questions into the Q&A panel at the bottom of the screen. You can send them in at any time. We'll collect them and address them during the Q&A session at the end of today's presentation. Now, I would like to introduce our speaker today. Brian Miller joined EPC in 2015, where he is the field applications engineer for half of North America now, East and North Central? Is that where?
Something like that.
He has over 30 years of experience in power electronics as a design engineer and as a field application engineer. At IBM and Sony Ericsson, he designed small, efficient power supplies and battery chargers for laptop, tablets, and other equipment, and designed a custom analog controller IC for laptop, DC-DC, and battery charging. Previous to EPC, Brian was a field application engineer for Semtech, where he was involved in designs for AC-DC, DC-DC, LED lighting, and other areas. He's authored patents, articles, and talks, and Brian received his MSc and BS degrees from Duke University in Durham, North Carolina. Brian, thank you for joining us today.
Well, thank you, Renee, and thank you to everybody for joining in. I guess I'll start the talk here without any further ado. Yes, like Renee said, first time right. We'll explain what that means for controllers, gate drivers, and so forth. Now let me go page down. There we go, an agenda. So first review of EPC GaN FETs and ICs. What are they? What's the big picture? GaN first time right, what that means, how it can help everybody. Controllers, gate drivers, and layout tips and layout examples, including a little shortcut at the end of how to possibly save a lot of time with layout. Okay, EPC products. So EPC makes power transistors made of GaN, which is a material superior to silicon. The range that EPC makes for GaN FETs is 40 volts to 350 volts, from very small, like less than 1 by 1 millimeters, and less than a half an amp, up to about over 100 amps continuous. So here's a display of them here. So to go into a bit more detail, package types. The one that everybody tends to associate with EPC is chip scale, and the chip scale covers the full range of voltages. It's all sizes except the largest. What you're looking at is the actual design. You can see the lines down here. Over top is polyimide and so forth to protect the active area. So it's a sealed chip scale part, and this part goes down on the board, obviously. The other one that's relatively new is packaged. So QFN packaged GaN FETs. So from the bottom, you see the contacts. From the side, you can see how it can wick up some solder. On the top is actually the exposed substrate, which in the case of GaN FETs from EPC is silicon. And these have gotten a lot of interest lately. So to go into a bit more detail, here's a little chart of them, 100, 150, 200 volts, different RDS-ons, including down to 1.0 milliohms typical. And just a few little details. They have excellent thermal conduction. A lot of them have 0.2 degrees C per watt, high current ratings, and so forth. And many people say they're nice because it's easier to solder them and to see whether they're soldered. So those are the two types of FET packaging we make. Also, integrated circuits made of all GaN. So they're all GaN, one monolithic die. That's another part. There's FET plus driver, typically smaller, typically for pulsing lasers, can be used for boost converters, but mostly for non-DC-DC applications. For years, EPC has made half bridges up to 100 volts. But more lately, thinking, well, if you look at the top of the power stage, which has the gate driver built in, that seems more attractive than just a half bridge without. So in the future, probably see more of the power stages being released as a focus. Here's a bit of what's inside. I won't go into details, but just everything: level shifter, a dual gate driver, three different models here, plus another one with an external bottom FET. But if you're interested, it might be interesting to go to EPC's website and type in one of these part numbers to see. Another introduction about GaN FETs, they're kind of like MOSFETs, except they're smaller. They switch faster, and that means they switch more efficiently. So you can switch them, the transition time where power is lost is much faster. They do have reverse voltage conduction. This is the EPC diagram that shows a diode going back, but it's not a real diode. It's not a parasitic element. It's not a troublesome PN diode like in silicon MOSFETs, but it's actually the main channel conducting. So it's nice that there's zero reverse recovery in a GaN FET. And the Miller ratio is designed to make it so you can switch fast without having a worry of the part switching itself back on after switching off. And there's exceptional reliability. Just as a comparison, I mean, my goodness, look at a 200-volt silicon MOSFET versus a GaN FET of roughly the same kind of RDS on. You see something like 15 times smaller, no reverse recovery. And this kind of explains a lot of the appeal of GaN FETs. I'll keep on going. Zero reverse recovery, you can say, well, what does it mean? Here's a silicon MOSFET switching, different kinds of dead times. You see different kinds of ringing. Versus a GaN FET, you can see much less ringing, much less amplitude on the ringing, much better controlled. So even though the GaN FET is faster, you can slow it down a bit. If you get the equivalent kind of switching speed, you can see much better performance. And Miller ratio, that's just a illustration of how it stays below the line of 1. Okay, now let's move on to the GaN first time right. What is that? That is a process that helps with the design process. So in other words, looking at GaN, there's all kinds of information, lots of tools, lots of application notes, how to get these all together, how to make them so they're usable to people, with the goal of being a smooth product development with excellent performance. So there's 3 basic areas of research. You can see different design examples that EPC has, and also other partners have design examples also. And you can refine it if you'd like to by changing the device used, the FET used, to something that's more suited to what your particular needs are. The second part is design. So we have examples and also lists of drivers and controllers, and some schematic and layout examples and tips. A loss calculation. That's kind of important because you'd like to know how efficient something is, but also for the next point, which is thermal management. Now, GaN FETs are more efficient, but still, there's always heat. So how to remove the heat, how to deal with the heat is a very important topic. And lastly, evaluate. So once your design is over, how do you tell the manufacturer how to assemble the GaN FETs? And also measurement, how to verify your design is like what you'd like and how well it performs. Now, we're not going to cover each one of these in detail today. It'll probably take a lot of time, but as the title said, concentrate on a few areas. One is design examples. And these really help with things like a layout and schematic and so forth. So evaluation boards, they come with documentation. Here's a link to a chart of EPC evaluation boards for DC-DC. What's also nice is there have been several companies such as TI, ADI, Renesas, Microchip, Richtech, and others that they have partner reference designs too, which we list at the EPC website. Now this presentation will be available after this presentation, after this session, I guess in a few days. So you can click these links later, but they're also on the EPC website. These boards cover buck converters, boost converters, buck boost converters, LLC, and other types of designs. For example, if you type in, if you're interested in a buck converter and you go to that chart, you'd end up with this. So it shows a of range of power. This is strictly buck, and you can see that there's some different analog controllers. There's analog devices. There's Renesas. Others have digital controllers, and it gives you an idea of what it is: one phase, two phase, single output, or dual output. And that's what one of the boards looks like: a relatively small square board with inputs and jumpers. Right over here, you can see jumpers you can configure to do what you want. The information for these boards is available without purchasing the boards. You just go to the website. For example, in this one, you type in the number 9195, you could see schematics and Gerbers and layout and so forth like that. First example, just a single buck. So Analog Devices has made a very nice controller. It's a made-for-GaN buck. And what's interesting about this is it can take the switch node, feed it back, and minimize dead time all the way down to 0. Now, you may or may not like to do that at first until you get more familiar with it. That's switchable. You can switch that on or off. Very nice feature. And you see the GaN FETs right here, a nice driver with 2 outputs. Anyway, there's a made-for-GaN buck controller and a board that goes with it. Analog Devices has a board too. Here's some details on one of the boards. In this case, it's an EPC board with that same basic controller. This is the dual version. But you get the idea that, for example, if you have 28 volts coming in and 12 volts out, then here's 98% efficient, which is very good, actually. And that's not a ZVS. It's a hard switched buck converter dual phase. Down here, you see a thermal image of it. This over here is not efficiency, but actually power lost. So you can see with different inputs how that affects the output power lost. The interesting thing about this is it's not even EPC's latest GaN FET. So there's a possibility of increasing the efficiency even further by using a new GaN FET. And we'll get into a bit later, like how would you know or how would you find out such a thing? Example number 2, a boost converter. Renesas has a nice dual phase boost converter. And again, this is made for GaN. Their data sheet shows circuit implementations. EPC has a reference board. They have a reference board also. This shows efficiencies also for the state of 48 to 12 at different currents. A lot of people ask about high current, whether for automotive, whether for industrial or so forth, large currents in a relatively small area, but also efficient. So EPC has a series of boards, taking one of them, many of them very similar. This one, what they do is they do 1 kilowatt per phase when going from 48 to or from 12 volts. So you can run it as a buck, or you can run it as a boost. Not a 4 FET buck boost, but either boost or a buck. Has a digital controller. There's 2 phases for boards. You can link the boards to multiple phases. So I think with boost, you can go up to 6 kilowatts by linking boards. With boost, I think up to 4 kilowatts by linking boards. They run at 500 kilohertz, which is a good mix, a good match, a good compromise for EPC GaN FETs between high speed, which means lower size parts, and also very good efficiency. So you can see over here an efficiency plot going up to 140 amps output or 70 amps output per phase, showing this. And again, this design, like the others, is available. You can see the bill of material, the board design, schematic, and there's a quick start guide with various charts. That's where this chart came from, the quick start guide. So how to select the right device. I mentioned before you can modify the board. There's a few different ways. We have some various tools on here. And sometimes the new GaN devices are often the best performance and cost. So in many cases, if you pick apart and look at it some more, you can actually reduce the cost and increase the performance simultaneously. So to get to that point to look, EPC has a buck converter GaN selector tool on the web. A boost one's coming soon. With this one, you put in input, output, current, frequency, so forth, and it'll rank the FETs according to FET efficiency. So for top FET and bottom FET. I won't demonstrate it here for because of time constraints, but these are part of the GaN First Time Right website that EPC's marketing people put together. There's also a cross-reference where you can enter a MOSFET and you can get a GaN FET upgrade. So you can see if you enter a MOSFET and then you change some of the parameters to what you're doing, say a buck converter with a particular input and output and a particular frequency, what a GaN FET can do. So it'll show the heat dissipation and also digikey costs right on the tool, which is kind of convenient. And that's what it's supposed to say here with heat and costing. There's also a thermal calculator, and that's really interesting. You can see the difference. Do you need a heat sink or not? Can the heat conducted into the board do well for you, or should you put some kind of heat spreader or heat sink on the top? So these tools are very good to select the right device for your particular application. Now let's go on to controllers and gate drivers. So controllers for GaN versus a few years ago, now there's many controllers that are designed for GaN FETs on the market. Of course, two different categories. First is analog controllers. And the range there is buck converters, both single and dual. Boost, both single and dual. A buck boost, including another one for USB power delivery. And there's also synchronous rectifier controllers that can be used for GaN FETs. The other category is digital controllers. As you can imagine, anything you can think of with good programming and enough processing power you can do. These would typically require an external gate driver or a GaN IC with a built-in gate driver. So the analog controllers typically have the gate driver built in. Digital controllers is typically separate. Here's a few. This is not the exhaustive list, but here's a few controllers that are out for made-for-GaN. A single buck controller, a dual buck controller. Using this board, this is the intersil part, ISL 81806, you can see a graph of efficiency for that board. And there's a list on our website for things like synchronous rectifier controllers. And there's additional GaN controllers in development. If you have a function you don't see or you need, you could always ask your favorite controller supplier if they could please do one for GaN. That's the way some of these came about. Some design engineer, like some of you on the phone, would say, "Hey, how about for example, a single buck controller that's optimized for GaN?" And things happened, and the controller came out. Oops, let me go up again. Yeah. So there's quite a few gate drivers made for GaN. It's really quite a list. To go over some of them, there's single drivers. There's some ultra fast ones, which are useful for a lot of applications. And they're also ultra small too. Some with or without LDOs, and some are one that's isolated. There's a lot of half bridge drivers. There's the first four are all in the same common footprint, which is kind of convenient. The next group is automotive qualified ones. The next group is higher voltage, but also some special features. And the last one is isolated. So from isolated to automotive to high voltage to low voltage to multiple sourcing, there's quite an impressive lineup of GaN gate drivers. It would probably be too much to cover all those today. So just a few um, interesting tidbits on some of these. Some have a PWM input, a single line input. Some of these you can either put two lines in, like for top FET and bottom FET, or just one line, and the gate driver itself can control the dead time. You can have very small dead time with GaN FETs, and some of these gate drivers can actually help control that to optimize the performance. Current sense resistor. There's some designs where you want a current sense resistor in series with the bottom FET, in series with a source going to ground. Now you might say, well, isolated gate driver might be good, but there's also some drivers on the market where you get, say, about plus or minus 5 volts worth of floating on the bottom gate driver. The goal is to keep the sense resistor out of the gate drive loop. So you have a gate driver loop and you don't want the current sense resistor in there. And some of these gate drivers can help that. Some have 5-volt LDOs, because 5 volts is about the ideal gate drive voltage for GaN FETs. For EPC GaN FETs, 0 volts is off, 5 volts is on. No need to go to negative voltage, and not much advantage to going above 5 volts. Also some very high speed ones, probably much higher speed than anybody would ever need, and other features. Okay, now to get into some layout tips. And the first thing you might ask is why? Well, there's some different advantages of good layout for GaN FETs. One is efficiency. As the energy goes into the path you want it, the efficiency goes up. As efficiency goes up, the thermal situation gets a bit better. And not just that, but if you do different placement and layouts, you can actually improve the thermals on the board, which is nice to see. And also with good layout, you can reduce the ringing and reduce EMI. For years, EPC has had an optimal design app node and boards that are based on that. More recently, there's variations on that, which might be interesting to see. So you can modify your board to get slightly different, to meet different goals as far as the placement. And also, once again, thermal. So kind of a quick review. This is maybe the example where you'd have over here, you'd have a digital controller, or maybe this is the output of an analog controller with a built-in gate driver. Excuse me. There's a few parasitic inductances all around. One you'll see is common source inductance on each FET. The problem with this one, it goes in both the gate drive loop and the power loop. There's the power loop inductance going around here. It includes the external inductance and so forth on the bypass, and board layout too. Not just the components, but the board layout. Next is gate loop inductance. And you see there's a different path for turn on because the energy comes out of the gate driver capacitor, goes around through the gate driver and over to the gate, and a different one for turn off, where it's mostly contained in the gate driver. It just basically shunts the gate drive resistor down to the common point, or down here, basically to ground. So there they all are, and it's quite a bit. And we'll go through these and see. And then again, at the end, the little shortcut that might be useful for some people. So you could say, okay, common source inductance, still, does it make a big difference or a little difference? What are we talking about? And yes, it can make a bit of difference here. This is a board, maybe not common board, but a board at 1 megahertz with low voltage. Here's the power loss in watts. Parasitic inductance, you can see down at 0. It's like a baseline. As just the parasitic inductance goes up, everything else being equal, you can see the power loss goes up also. This shows the power loop inductance. Not quite as drastic of an increase, but it's still there. The not so nice thing about inductance in the power loop is you can see overshoot on the voltage waveform on the switching converter. The same exact FETs, same exact schematic, just with a better layout, you can go from 70% overshoot to 30% overshoot. And this superimposes the common source inductance loss on top there. So the impact of the gate loop. And of course, two loops in the half bridge, the top and the bottom. And you really want a resistor to damp ringing. It does slow transition, but even something like a 1 ohm or even a 0 ohm resistor, sometimes there's no such thing as a complete 0 ohm resistor, then that can certainly help too. It allows you to tune the gate drive speed to what you want by having this resistor in your board layout. Of course, this is just a parasitic element here, the L, of course. EPC does not recommend you putting in beads in the gate drive path. Here's some comparisons. So years ago, EPC did a comparison. How about if you take the same schematic, same FETs, just use 3 popular layouts and see what the difference is. So the first one is one like many people instinctively would say, okay, everything goes in the top, you make a loop, you put them all together. So there's the decoupling capacitors, top FET, bottom FET. Next one, what happens if it goes vertically down through the board? So you put the capacitor down here, so less total area in a vertical kind of way, and the current just goes down. So it moves the loop to be a vertical loop. The last one is what we call more optimum loop, where it has similarities to both, but on the top you have decoupling capacitors, then the top FET, then the bottom FET, and the first inner layer of the design. Whoops, the automatic speed was on. The ground return from the bottom FET goes in the first inner layer, and then makes a nice narrow loop. It really reduces the total inductance. It shows coming from this point at the end, but many FETs have pins in the middle. So the gate loop of the return ground loop can actually start in the middle of the bottom FET in many cases, go down and around. So here's a showing what difference it makes. First, the lateral one where everything's on the top. That's the green. You can see the inductance is kind of high. And it really depends on, that's some interlayer thickness. The external one where it has at the bottom, that really depends on the thickness of the board. You can see here, as the board thickness goes up, just how much this increases. The internal vertical one, where it just goes into the first inner layer, you can see here, first of all, it's lower. As the board gets thinner, the difference between the top layer and the first inner layer, you can reduce from the dashed line to the solid line if you're able to do that. Here's a little showing here. And again, you see the solder, the copper, the core, more copper. So between these 2 copper layers, that's the key for this. And that's, sorry again, the animations here. And that's clearly the best choice. So designing a low inductance one. And this is the one with the up, down, and you can see different vias here. Not too many vias because you still want the ground to be relatively free so the current can flow in the first inner layer. This is the first inner layer. This is top layer. And you see the nodes labeled. Nodes are kind of big, so the nodes, the planes here can also remove heat. So having a big plane for electrical and thermal conduction is good. So the idea is place the components as close as possible. Place as many vias as you can close to the innermost electrical connection. Thin as possible substrate. So if you can make this thin, the distance thin, that really helps reduce the vertical depth of the current loop. and spread out via connections at the innermost connect. You don't want to block any of the current from flowing between the vias. And again, the ground conductor here, this is ground plane. It doesn't need to carry the full current. This is a return. You probably have other layers down in the board, probably have parallel layers that also that carry current. These are more for the high-speed transients. Now, if you take the basic layout, you can change it. So you can move, there's 3 elements, you can stack them different ways. If you take the capacitors from the top and them at the bottom, then the top FET is not between the capacitors and the low FET. This could be good for getting heat out of the top FET if that's an issue. The other way is you turn things around is put basically the capacitors in the middle. So you separate the 2 FETs. What this also does is it puts the switch node buried inside the board. So this green, this is the switch node. The red and the brown, I'm sorry, gray. The red and the gray are basically DC, not much noise on these. But the switch node is where the transitions are. So that's buried. That could be good for EMI. Okay, now switching from the power to the gate drive. Again, this shows what we did with the power, but over here is the gate drive. So using a return polygon on the next layer, there's a bit more flexibility with the gate. You want to take it out and go down. One interesting key a lot of people don't really think about, and I didn't until I joined EPC, is that the top FET, of course, its reference on the source is the switch node. So on the first inner layer, you'd want to have a switch node. That's the shield. That's the reference sign. That's the common point for that gate driver. So instead of ground underneath that part, and you can draw the shield right underneath the gate driver itself. So the bottom is shielded by ground. That's what the reference is for the bottom FET. Top volt reference is a switch node. So those really help with the gate drive. Okay, simplifying GaN layout. One idea we have, which is some of our new ICs, the power ICs, you notice this has the built-in FETs and gate driver and so forth, but it's a monolithic die, so you look between these and there's almost no room, which is good. The connections are basically right there, so there's not much possibility of having inductance inside the chip itself. The gate driver is put right there, so the gate drive loop is very self-contained, both on top and bottom. And the power loop, the only thing that is external is the decoupling capacitor. So laying out this one capacitor here, or multiple capacitors as needed, between the VN pin and the ground pin really is a real good, real good start to having a very good layout because the layout is contained within the IC. This is the series 2310X series, where X goes from 1 to 4. And they're 100 volts, 15 amps to 65 amps, again, with the internal GaN gate driver. So if that type of thing works, and if the reading through the data sheet, it looks like it's good, then that can really help with layout. You can still control the speed. So right here, there's a resistor for the top. There's a resistor for the bottom. These are basically speed control resistors from extremely fast to slowing them down just a little bit. And again, layout tips, just the decoupling capacitor. And also put the ground on the first inner layer. So put this down on the board, ground underneath, and decoupling capacitor put in. And there's some example designs EPC has for this, either for a complete closed loop controller, the buck controller board, or a half bridge board, where the layout might be interesting to see. Now the question comes up also, well, you know, there's a gate driver in there. If you have an analog controller, a typical analog controller has built-in gate drivers. Do you really want to duplicate gate drivers within analog controller and also within the IC? And sometimes the question is, yes, it's not that big of a deal. Analog controllers without gate drivers, I don't think there's a huge amount of choice. Maybe there's some that I don't know about. Maybe you all have good ideas. But even if you have a gate driver, it probably doesn't add that much to the cost or size of it. But in either case, having an analog controller and some lines coming out going into the power stage, and then out to inductor and output capacitor. This is the input capacitor, output capacitor. And this can work for either buck or boost with those kind of controllers. So for benefits here, you'd have the fast, efficient, and small DC to DC. Some controllers can work up to 3 megahertz. I think the analog devices ones made for GaN work up to 3 megahertz. I'm not sure anybody in EPC has actually done that. These power stages work up to 3 megahertz also. So it'd be interesting if somebody wants to try it, put those two together and see if that's a good idea to make a very small, compact, high-speed DC-DC converter. So it's small number of parts. And again, simple layout where the most complicated part of the layout is within the IC. Some of the things you might ask as a separate topic, what to look out for when you're doing a GaN FET design. If you've been doing some designs with silicon MOSFETs, what kind of things, just a few, what kind of things should you kind of pay attention to? And we'll go through that layout. So we just talked about layout. You can get more out of GaN FET when you optimize the layout. Thermal design. That's something that is key. GaN FETs have very good conduction to the top, but because they're small, using the thermal calculator the EPC has and looking at some app notes can really give a help in doing good thermal design. GaN FETs conduct heat through the top, also from the bottom, but because the top area is larger, they conduct better out the top. In manufacturing chip scale parts in high volume, that's something else. Now you might say, well, I like your QFN package parts better. In that case, you don't have to worry about number 3. But just going through that, and again, there's app notes for the manufacturing of chip scale parts in volume. And EPC has experience to help with these issues. And for all these, not just experience, but also app notes, example designs, and so forth. And here's some if you'd like to reach out for some help or have a question or so forth, there's the Ask a GaN Expert link. There's a technical forum that we're doing. And again, the cross-reference is useful. That'll get some ideas as far as maybe perhaps a starting point versus, not just versus MOSFETs. If you type in an EPC GaN FET, you might be able to see others that are very close to it. So here's the list of the Summer of GaN webinars. I think, Renee, I think you arranged all these. You put the schedule together for these. The next one is, looks like August 21st.
Yep, that will be the last one in the series. And the other ones, if you missed any of the other ones, they're all available on the website to watch on demand. So let me just say thank you, Brian.
Well, thank you. Thank you all.
Now we will start answering some of the questions that have been submitted. And as a reminder, you can still go ahead and submit those into the Q&A function, and we will we'll get them answered. So our first question is, does bootstrapping work well for driving high side GaN switches?
Yes, it works very well. With the caveat that it's good to regulate the voltage on the high side. That's actually a very good question. We go back there to some of these. Well, I could use this example here.
Mhm.
Inside the typical driver, whether it's an IC or like for example, even the TI driver, they regulate the top. So you might think, well, bootstrapping, is that a good idea? Yes, it is, because there's a limit in most of these LDO or some kind of limit that has an ideal output for the top FET.
Okay. Can you recommend some bootstrapping diodes for 400 volts?
Hmm, that is a good question. I would say that some of these drivers, for example, the onsemi one, have built-in LDOs for the top, and they assume you're going to boost something like 12 volts, and they assume you're going to do that, and then it regulates itself down to 5 volts internally. So in those kind of cases, you don't have to worry about a low drop. If you're asking about, gosh, a Schottky at 400 volts is pretty bad, or some other diode is pretty bad, I think it's okay, and it doesn't need to be very high speed either. There's capacitors there. So as long as you're not trying to switch very high frequency, like over megahertz at very high voltage, um, I don't think it's all that critical. One where it is critical is for a TI 200 volt gate driver, but they have excellent documentation in their data sheet as far as recommended part for that one.
While calculating efficiency of a converter, how do you measure the input power? Is it from source display or through oscilloscope?
I think it's from the source using a voltmeter on the voltage and a current shunt measuring the current. So the total input power going into a board. In some cases, if I can go up a little bit, um, some use the housekeeping supply as part of it, some don't. I think up here where we show the efficiency was a difference of efficiency. So I think the housekeeping and other kind of parts were not included.
Okay.
But typically not an oscilloscope for the input power, more of like I guess a DC type of input power.
Does EPC make high temperature GaN HEMTs for about 175 or 200 degrees C?
No, we don't. We don't. And that's a good question. I know what you mean. Like for the we set 150 volts max. You might say, well, gosh, GaN is um, a kind of device that can stay as a semiconductor at very high temperatures. And that's true. EPC has done some work at very high temperatures, but the design of the FETs was done to optimize characteristics at 150 volts and 150 degrees C and below. So no, it's not optimized. It's not designed to go over 150 degrees C.
Um, okay. EPC power stages are rated in amperes. Typically, they are top driver. So, like the EPC 23101 is rated to 65 amps. How is the current rating specified? Is it the RMS current on the top FET or on the output current on the converter, like a buck?
Yeah, it's the output. Output. It's like a guidance. As these get into production, there'll be more specs as far as the FET by FET. But the short answer is it's output based on a few things, based on the um, current capability of the internals, based on idea of thermal limitations and so forth.
You mentioned no need to go to negative voltage to turn off. Then why do people worry about spikes that may turn on the FET?
Hmm. Yeah, that's a very good question. First of all, yeah, that's true. Negative voltage, um, we never use it and we don't recommend it because it's more trouble than it's worth. And a negative voltage actually increases the voltage drop of the return path, the diode function. So the question is, well, if you don't have that, there's not much margin between, say, ground and the threshold. Few answers to that. One is with a good gate drive, you won't have that kind of problem. If you can have a minimal loop and GaN FETs are small, then that won't be a problem. If it is, then the GaN threshold knee is not as sharp as it is with MOSFETs. So if you go into the threshold, which you shouldn't do, but if you do, then it doesn't mean everything falls apart right there and it cross conducts and blows up. Means the leakage gets worse there for a bit. And another thing that should help add some confidence is the gate threshold doesn't really drop with temperature very much at all. Definitely does with MOSFETs. So if you see something like a 25 degrees C spec on a MOSFET of, say, 1 volt, you would rightly get concerned because you would think, well, gosh, 100 degrees C, that threshold's going down, the gate and the noise margin is gone, it's going to blow up. Versus GaN FETs, the same threshold voltage is basically the same at 25 degrees C and also, say, 125 degrees C. So the margin doesn't go away as temperature goes up.
For the integrated sync bootstrap device, is it a MOSFET or is it actually a tiny GaN device?
I think person's talking about the GaN IC.
I think the integrated one, right?
Yeah, let me go down there again. Perhaps talking about this one right here, the sync boot, I think, in the diagram. Yeah, everything in this blue box right here is all one monolithic GaN IC. So everything in here is a GaN FET. These FETs are the power FETs, 100 volt FETs. Some of these are low voltage FETs. This one has to withstand both, so it probably isn't low voltage, but some of the parts inside the gate driver are lower voltage. You can have a difference of voltages within one GaN IC. But yes, this is a GaN FET in here.
Can you elaborate a bit on better heat dissipation and EMI issues for high voltage, high power, and high frequency applications?
Let's see, for high voltage, I guess depends what it is. I guess for EPC, it's 200 volts is what we typically say is the top. People have done multi-level.
High power, I think they're talking kilowatts.
Okay, we go back up again, maybe to that one board. It takes a while to go through the animations to go up here. And there we go. Here's one of the high power boards. And the question was, can elaborate more on heat? Yes, that's a good question. On this board, you can hopefully see there's a white ring or white rectangle. That's actually outline of a heat sink. Inside there, you'll see these four, at the corners, you'll see these round things, look like screw holes. They are screw holes. They're cheap little screw adapters from DigiKey. They just happen to be 1 millimeter tall. If you put something on top, like a heat sink or a heat spreader, all the GaN FETs are less than 1 millimeter. So a little thermal pad sitting on top of here. These take the mechanical stress, and then the heat sink goes on top of that. Either heat spreader or heat sink will go directly. And that's probably the best way to get the heat out the top, using a heat spreader or heat sink, and also using external spacers to keep the pressure directly off of the GaN FETs. Let's see, that was for heat. You mentioned something else?
EMI.
EMI, yeah. Well, I guess it helps to have, you can ground the heat sink if you'd like, because you need insulation, electrical insulation anyway, for a top FET and bottom FET. So that's possible. So you can kind of encase it there. So having that, plus having some inner layers of the board. But another point is the inductors. You might think, well, inductors are inductors, but there's some companies, one company is Worth Electronics. They make some inductors that are actually kind of polarized. So one is meant for the switching node, the other is meant for the output. Switch node is closer to the ground plane on the board, so there's less distance. So reducing EMI through the FETs, through good layout, but also through inductors can also help to keep all the loops small, to keep high-speed nodes as close to the board's ground plane as possible.
Okay. All right, we have a couple of minutes if anybody else has any other questions. Otherwise, Brian, thank you for this presentation. Thanks to everyone else for attending. If you think of any questions after we hang up, you can send them into info@epc-co.com or to the Ask a GaN expert on the EPC website. You should receive an email in 24 to 48 hours with a link to view a recording of today's webinar, and also the presentation slides will be available as well. And lastly, Brian mentioned the last installment of the Summer of GaN is scheduled for the 21st of August at 10 a.m. Pacific time. And the topic will be GaN first time right, and it will be a focus on the web-based design tools that Brian mentioned today to accelerate your time to market. So we'll provide an overview of the GaN first time right design process, which is a step-by-step framework to maximize the potential of GaN FETs and ICs. And we will demonstrate the web-based design tool specifically designed to facilitate the seamless integration of GaN FETs and ICs into any power conversion system. This webinar is great whether you're new to GaN or looking to refine your designs. The registration link is available on our website at epc-co.com. Thanks again, everybody, and have a great rest of your day. Thanks, Brian.
Thank you, Renee, and thank you, everybody. Bye.
Bye.